Hi, my name is Reyne from the University of Sydney, and I'll be going through practice problem sample N. Now, as I have done previously, the first thing I do is look at these tests up front, and straight away, they are all negative. We don't see any unsaturation. There's no reaction with the bromine. We don't see any oxidation. There's no reaction with the acidified potassium dichromate. And when we add sodium carbonate, we don't see any bubbles. So that tells us that we're not looking for any double or triple bonds. We're not looking for any alcohol or aldehydes. And we're also not looking for any carboxylic acid. Now, this doesn't rule out everything, but it tells us that those won't be present. As with before, I tend to skip IR and mass spec, and I'll come back to those afterwards. So let's jump on down to our carbon and our proton first. Now, in our carbon, we can see a total of 4 peaks. So let's kind of label these and have a chat about them. So 1, 2, 3, and 4. And if we think about what we know around the positioning of these peaks, we know that as we move from right to left, so increasing from 0 towards 180 on the scale, that's indicating how de-shielded our carbon environment is. So for instance, peak 1, that carbon environment is very de-shielded, extremely de-shielded. So this suggests attached to more than one oxygen or similar electronegative species. Okay, so that carbon must be attached to something very electronegative, and in fact, likely a couple of electronegative things. Peak number 2, similarly, is at about a ppm of 60, which to me would suggest that it's likely attached to something electronegative. So often that can just be one oxygen, can be other things, but most commonly oxygen is kind of quite a prevalent theme in a lot of these kinds of compounds. Down to peaks 3 and 4, we see they're roughly around 20 ppm. So for these, it's kind of suggesting to me that they're not so close to electronegative species. So they're going to be maybe more of a tailing off end to a compound or something that's a bit removed away from something that's electronegative. We can also think about the heights of these. They're all about the same. As I've said before, when it's proton NMR, we think about the area under the peak, and that's really important because with like multiplicity and having multiple peaks inside of the one or multiple spikes within the same peak, that's important for working out the ratio. But for a carbon, we can normally rely on the height to kind of indicate to us the ratio of these environments. Now in the proton, and we'll use the different labeling system, we'll use A through C, we can see 3 peaks here. So we have peak A, which is a nice looking quartet up at about the 4 ppm, again, downshifted. So therefore it's got something next to it that's pulling away electron density. We can see a singlet at peak B here at about 2 ppm. And we can finally see a triplet at peak C down at about the 1.3 sort of area. Okay, it's about as much as we can pull out from just looking at that. And that's where we want to shift our attention down to this peak data table down the bottom. Now, as we've done before, this can kind of tell us a little bit about the number of protons that are, or the number of hydrogens that are in each of these environments. So for instance, the quartet peak A at about 4.12 ppm says to us that there are 2 hydrogens in this environment compared with say 3 at peak B and then 3 at peak C. Now, as I have mentioned before, and something you should keep in your mind is that these ratios don't necessarily mean that there are only 2 hydrogens, 3 hydrogens, and 3 hydrogens. It's the ratio that's important. So we might start by going with the simplest ratio to propose an initial structure, but we may have to reevaluate that later. Now, at this stage, we kind of have an idea of how many carbons there might be, how many protons or hydrogens there might be. So let's move on up to the mass spec, and we'll deal with this one next. Now it's telling us that we have a molecular ion mass of 74, mass to charge ratio. Now that 74 is great. It can kind of really narrow things down for us. So let's say, take the most simplified approach. Let's say, assume that there are only 4 carbons present, 4 different carbon environments. We're assuming that there are only 4. That would suggest 4 carbons, tells us 48 to go towards that 74. If we then look at our proton NMR, we can see there that there is a total of, simplest ratio again, 8 protons present. So we've got 8 protons present, which brings us up to a total of 56. Okay, now that's a bit shy, all right? It's a little bit shy of what we're really after. And right now, we don't really have much more information. All of the tests at the front didn't narrow down what functional groups are present. The carbon and the proton suggest that there's something electronegative, but we're not sure what. So before we progress any further with the mass spec, we might actually turn and have a look at the IR. Now the IR is really quite important because it can tell us a bit about what species or what functional groups are present. It doesn't tell us too much about the structure, but it can tell us, is there an alcohol present? Is there a carbonyl present? So on and so forth. Now, there's a couple of things we can rule out. For instance, when we see this peak at about the 3000 mark, that's typically going to be our carbon-hydrogen stretch. When we see this peak at about the 1450 mark, that's typically going to be a CH bend. Now, what's great is seeing this really sharp peak at about the 1700 mark, 1750-ish. That is telling us very strongly that there must be a carbonyl. So a carbonyl is a C double bond O, and that could mean that it could be the carbonyl that's in an aldehyde, a ketone, a carboxylic acid, an ester. They all feature a carbonyl, but we've already ruled out an aldehyde. We've already ruled out a carboxylic acid. So now we're down to the idea of, is there a ketone or is there a ester perhaps present? Now, normally down in this sort of region down here, the fingerprint region, we don't really deal too much with that because it's kind of quite hard to really pull apart that information. There's a lot of carbon-carbon bond movements that really confuse and blur that area. But we do have this other nice peak here. It's kind of getting down towards the fingerprint region. So normally it might be a bit messy and hard to see, but this particular case, it's quite stark, stands out. And if we consult our table earlier in the document, you'll find that this relates to a single bond carbon oxygen, which is interesting because this is suggesting then that there is both a carbon double bond oxygen and a carbon single bond oxygen signal for this structure. That would rule out a ketone, unless maybe you had a bridging carbon further along the chain sort of thing. But now here is when we want to try and go back to some of the early information we saw. This is suggesting that maybe there are 2 oxygens present, and down in our carbon NMR, it looks like there's a carbon environment that's being influenced by 2 electronegative species, which could be both of these. Also, if we then think about, I think there's an error here actually. If we think about there being 2 oxygens, okay, that would suggest 32, which would then bring us, those 2 together, that would bring us more up to 88. And in fact, there is a peak there. You might have to change that. But that would tell us that our mass to charge ratio should actually be 88, which then matches up with our 2 oxygens being present. So if we try to put this all together now, okay, we can kind of maybe start in the middle and say, well, there must be a carbon, right, that has a double bond oxygen, and a single bond oxygen coming off of it. Now, there are 3 other carbon environments present. Of the 3, peak 2 suggests that there is another carbon attached to our attached to an oxygen, all right, or to an electronegative species. So that must be here. So now we're at the stage where we need to think about where can we place these other carbons that need to go around this sort of central ester sort of feature. So here we need to kind of think about our protons then. All right, we have 3 different proton environments. We've got a singlet, we've got a triplet, and a quartet. Now a singlet suggests to me that there are protons present that don't have any neighboring protons around it. Now, the only way that would work would be if, for instance, there is a terminal carbon on the right-hand side or on the left-hand side. But then when we start to look at our peaks A and C, A is telling me that we've got something that has 3 protons near it. It's a quartet, the N+1 rule, but it's also de-shielded. So it must be near something that is de-shielding it, so near something electronegative. So I reckon that there must be 1 more carbon coming off of the right there. And if we switch to maybe purple, and we say that this is likely going to be our proton environment A, by that logic, if we have a terminal carbon or a terminal proton environment to the right of it, this must be C, because it's got a triplet, which means that there must be 2 protons nearby, which would be at the carbon immediately beside it. And with that information, we can finish up the last piece of the puzzle, that there must be an additional terminal carbon off to the left there. And that must be proton environment B. It's a singlet, meaning that the carbon next to it has no protons present. And that makes sense. That carbon's already used up its 4 bonds. It's got 2 bonds to the carbonyl, 1 bond to the oxygen, and then it's got 1 bond to the terminal carbon. For completion's sake, let's then match our carbon environments to this as well. So the carbon that is going to be most downshifted must be this carbon in the middle of the ester. The carbon that is next most downshifted, so peak number 2, must be that carbon next to the oxygen. And then it's really kind of hard to pick out of the 2 of these. So my suggestion would be that it's likely that the carbon to the leftmost is going to be peak number 3. And my reasoning is that it is closer to that ester central, or that ester functional group, than the opposing side over here. So it's likely to be a little bit more downshifted. So that would be how I would rationalize which of those peaks is which. Finally, if we're going to name this, we would then name this ethyl acetate. I think also that if you did the IUPAC name, it might be slightly different, but ethyl acetate is the kind of common accepted name for this particular compound. Cheers.